So now we know about confidence intervals and we know about hypothesis testing. In this lecture, we're going to consider the connection between them. Now, at first it seems like there really isn't much of a connection because their purpose is pretty different. Hypothesis testing is when we want a yes or no, whether we can reject the null hypothesis that a certain quantity equals a certain value, or we can't reject it. Confidence intervals are about what's a range of plausible values for the quantity. So they're kind of different. And indeed, we've seen, for example, we've done one-sided hypothesis tests and two-sided hypothesis tests, but we've only done two-sided confidence intervals. And also in the next week's lectures, we're going to see that when we have two samples, things get even more complicated and the relationship is even less clear. But despite all that, there is one nice clear connection between two-sided hypothesis tests and two-sided confidence intervals that we're now going to explore. As a first example, let's think one more time about flipping that bottle cap and it comes up either red or silver, and we had some data and we wanted to know the probability that it would come up red. So let's just remember what we said in that case about both the confidence intervals and hypothesis testing. So for the bottle cap, as far as hypothesis testing, we wanted to test the null hypothesis that the probability of getting red was just 0.5 versus the alternative hypothesis that it was some other value besides 0.5. How did we test that? Well, we first recorded our observations, which said we had 1,000 flips and our estimated fraction of the time we got red was 0.576. And in particular, that meant that the difference between the observed fraction and the hypothesized fraction for the null hypothesis was 0.576 minus 0.5, or 0.076. And then we want to know, is that value so large that we can reject the null hypothesis? Well, we said that we would reject the null hypothesis because we computed the p-value. And we said the probability that under the null hypothesis, H0, that you would observe such a big difference between the observed fraction of reds and the hypothesized fraction of reds was, well, we reconverted it to say it's approximately the same by the central limit theorem as the probability that a standard normal is bigger than some value, in this case 4.81. And we computed that that was an extremely small probability, about 1 chance in 650,000, which was much less than a typical significance level like 0.05. So we rejected the null hypothesis. As far as confidence intervals, that was kind of different. We said, well, the confidence interval, at least the 95% confidence interval, would be found by taking, well, our estimated fraction p hat plus or minus something. And in this case, that plus or minus was, first of all, 1.96, that magic critical value for the standard normal distribution, and then multiplied by the standard deviation. In this case, it was the square root of p times 1 minus p over n. And that gave us a certain confidence interval from 0.545 to 0.607. And we notice that that confidence interval, it misses the value 0.5. 0.5 is not in that confidence interval. So what does that mean? Well, there's two different things we can say. One is that we did a hypothesis test for whether 0.5 could be considered a possible value for the probability of getting red, and we said no, we reject that. Then we computed a confidence interval, and we said that confidence interval missed the value 0.5. So we kind of got a similar conclusion in two different ways. Is this just a coincidence? Well, the answer is no. We're going to see that this equivalence happens a lot more generally. For a second example, let's remember that human body temperatures data. So remember there we were testing whether it's true that the normal human body temperature is equal to 37 degrees Celsius, and we were comparing that null hypothesis to the alternative hypothesis that mu is not equal to 37. Now again, this was a two-sided test, and again we had some observations. In this case, we had 130 different human observations, and the observed value of the difference between the mean that we got minus 37, our hypothesized value, was this 0.19487, and we also had an estimate for the standard deviation S. And again, we decided to reject the null hypothesis that the true normal body temperature was 37 degrees, and we rejected it because, again, we computed a p-value. In this case, we're saying, what is the probability that the observed value of x bar would differ from the hypothesized value, in this case 37 degrees, by as much as it did in our own observations? And we said, well, in this case, remember when we rewrote and divided things, we converted it to something involving a t-distribution with 129 different degrees of freedom. And we said it works out to be the same as the probability that that is bigger than 5.455. And again, we computed that was extremely small. That was like 1 chance in 4 million, which was much less than a typical significance level like 0.05. So we rejected that and we said, no, the normal human body temperature is not equal to 37 degrees Celsius. We also could compute a confidence interval in that case. And in this case, it's a confidence interval for a mean, and we know how to do that. It's our observed mean plus or minus a certain value, which, well, for the normal, it was 1.96. In this case, because it's a t-distribution, it's a little bit larger. It's 1.979. And again, times the square root of the observed standard deviation squared divided by n. And that works out to a certain interval shown here, which, again, misses the value 37 degrees. So again, we can say that in this case, we could either consider 37 degrees to be a null hypothesis and we reject it, or we could say, let's look at the confidence interval, and the confidence interval misses 37 degrees. Again, is that a coincidence? Well, no. So now let's talk about the more general theory and be a little bit more abstract or general for a minute here. And so we can say, well, in general, if we had some hypothesis test, and let's do it for means, although it's pretty similar for proportions, we'd say, well, we're testing, say, a two-sided test. We're testing that it equals some value mu naught, whether it's 0.5 or whether it's 37 degrees or whatever, compared to the alternative that is not equal. In this case, well, we get some observations, some number n of observations, and some observed mean value x bar, and some observed standard deviation s. And we'd also get the difference. I'll call it d for now for clarity. So d is the difference between the observed mean compared to the hypothesized mean according to the null hypothesis. So then we're going to reject the null hypothesis H0 if the probability that the sample mean x bar would differ from the hypothesized value mu0 by more than the value d, more than the difference that we got. We'll reject it if that probability is less than or equal to alpha, whatever our significance level alpha is. Alpha might be equal to 0.05, let's say. And, well, we know that's the same as looking at, once we divide and so on, the probability that this difference divided by the square root of s squared over n is bigger than or equal to the corresponding value for what we observed. And then we say, well, that quantity on the left is approximately a t-distribution with n minus 1 degrees of freedom. And we want to know whether the probability that that is bigger than this value, d over square root of s squared over n, whether that probability is less than or equal to alpha. So that's the rule for rejecting according to the null hypothesis. Another way to think about it, which will make the connection to confidence intervals more clear, is to say, well, this will only happen if that amount of difference that we're saying is the probability that t is bigger than or equal to that in absolute value is less than or equal to alpha, if that difference is bigger than or equal to a critical value. So I'm going to write capital T now for a critical value, and this is the critical value which says that a t-distribution with n minus 1 degrees of freedom in absolute value, the probability is bigger than or equal to that critical value is equal to alpha. So this is a critical value, and again, that's the thing that played the role of like 1.96 or whatever in our previous calculations. And you can think of it as saying, well, this is the value where we'd be right on the edge of rejecting the null hypothesis or not. If the observed difference is more than this critical value, then we'll reject it. If the observed difference is less than this critical value, then we won't reject it. But on the other hand, if we consider confidence intervals, well, a 1 minus alpha confidence interval, so if alpha is 0.05, that's a 95% confidence interval. Well, for mu, well, it's our observed x bar plus or minus what? Well, that critical value, like 1.96 or whatever, times the square root of s squared over n. That's our formula that we had before. So when will that miss mu0, our hypothesized null value? Well, it will miss it if the observed difference, x bar minus mu naught, is bigger than or equal to this critical value times this square root of s squared over n. But if you think about it, that's exactly equivalent. It's the same thing, because if the confidence interval misses this value, so it means that this absolute difference is bigger than or equal to this value, well, that's exactly the same as saying that the probability that the p-value for the null hypothesis would be less than or equal to alpha. So we would then reject it. So in other words, it turns out, and if you didn't follow all this algebra, that's okay. It's just making a general statement related to what we already saw in the examples, that if you're just considering a single sample like we are so far, and if you're considering a two-sided test versus a two-sided confidence interval, then it turns out to be exactly the same thing at whatever significance level like alpha, if you say that you will reject the null hypothesis, or if you say that the corresponding confidence interval does not include the null hypothesis value. So in this way, we see that there are actually some connections. There's still kind of different ways of thinking. A hypothesis test is deciding yes or no whether or not we're going to reject a value. The confidence interval is giving a range of plausible values, but they have this connection that the range of plausible values will include a certain particular value if and only if that particular value would not have been rejected by the corresponding hypothesis test. So this is a way to think about these two different subjects as being in a way kind of the same.